So I'm really happy to welcome Professor Ulrike Kramm today here at our materials seminar. And I've known Ulrike now for a few years. Ulrike is at the Technische Universität Darmstadt. That's the Technical University Darmstadt. Darmstadt is a city a little bit south of Frankfurt in Germany. She has obtained her PhD actually in Berlin, which is quite far away in German standards from Darmstadt. And that was back in 2009. She then did a postdoc in Canada, and then she joined TU Darmstadt for what is basically an assistant professorship position. And then as of last year, right, 2020, she's now a full professor at TU Darmstadt. So this is great news and made me very happy to see that. She does great work in the field of non-precious metal catalysis and Mörs-Bauer spectroscopy. She has earned a bunch of prizes and awards, and the most two recent ones, and you can correct me, Ulrike, but I think the most recent ones are the Curious Mind Researcher Award from Merck. It's a big chemical company, and then from the DFG, which is basically our German National Science Foundation, the Heinz Meyer-Leibniz Prize. I think those were the two biggest sort of recent ones.
Yeah, I think so too. I lost control a little bit, but it's, yeah.
And I may have missed some, and then I apologize, but she's doing great work. She's being internationally recognized, and therefore I'm really happy that she's here and she's going to give a talk today in our materials seminar. As always, for everybody, please post your questions in the chat or tell me that you have a question, and then we will go through your questions after Ulrike's talk. And Ulrike, the stage is all yours.
Perfect. So thanks for the nice introduction. And I'm really happy that I have the chance to give here my presentation. As typically, not typically, but sometimes I forget to acknowledge the work of the different people that I'm showing. Therefore, I already wrote it down here. So the main part of the talk is related to the results that were obtained within a young researcher group that I have, funded by the BMBF. And it's related to the PhD students, Markus, Ling-Mei, Lotti, and Vladi. So this is Markus, Lotti, Vladi, and Ling-Mei. And but I will also go a little bit through some results from Stephen and Steffen. So this is Stephen and Steffen you can find here, basically. So I also thought to show you a little bit about Darmstadt. So at the TU Darmstadt, we have 3 different campi, one which is in the city center, then at the Botanic Garden, and the other one is called Lichtwiese. And this is basically the campus which is in the middle of nowhere. And you can see it here, and that's basically the campus where you can find all the different natural disciplines. The orange buildings are the ones where I have some labs or our offices, and here there will be a new building where I get then basically all my labs reunited in basically then one building, let's say. So this is a little bit older picture of my group, but of course due to COVID-19 it's very hard to take a nice group picture by now. So this is the outline of my presentation. I will of course start with a brief motivation. I will tell you a little bit about the catalyst requirements when it comes for the use of non-precious catalyst materials in fuel cells. I will talk briefly about the optimization of this group of catalyst materials. Then I will go into in situ Mörs-Bauer spectroscopy, and here we will see the condom again. And then I will go for the MNC catalyst materials for some further applications before I will conclude my talk. So I think this kind of introduction is not really necessary anymore, because I think every one of us is aware that the CO2 release into the atmosphere is one global problem, as of course it is strongly connected with the temperature increase that we have on Earth. And if we have a closer look to the different sectors where the CO2 is released, then we can see that the transportation sector, and this is the numbers for Europe, the transportation sector contributes to more than 20% in total to the overall CO2 release. And based on that, of course, we need also to find some CO2 neutral energy solutions for the transportation sector. And as you probably already know, the hydrogen fuel cell is one possible option in order to decarbonize the transportation sector so that then our Earth can still look nice and green and blue. In a hydrogen fuel cell, this is basically an electrochemical device. We have on the anodic side the hydrogen oxidation reaction taking place, and on the cathodic side we have the oxygen reduction reaction taking place. Both reactions require catalysts, and the state-of-the-art material for these reactions are platinum-type catalyst materials. So the catalyst accelerates the chemical reaction, and based on that we can gain basically sufficient energy out of the system. So that means what is shown here are the bipolar plates with the gas channels in order to transport the hydrogen or the oxygen to the catalyst layers. These are the catalyst layers, and to get a fine and nice distribution, there are here also some gas diffusion electrodes that enables a better transport of the gases to the overall catalyst layer. So as I already mentioned, the overall reaction product is basically water. So this is something nice, as of course it helps to make the energy renewable. So I already mentioned that here we need basically the catalyst material, and as you can see here, I highlighted the cathode catalyst material, because that is basically that part where we would like to insert our new and non-precious catalyst materials. And why would we like to do so? I mentioned that the state-of-the-art catalyst materials are platinum or platinum alloy catalyst material. And if we have a closer look related to the platinum mining, then we can see that most of this happens in South Africa, Russia, and Zimbabwe. And based on that, we have, of course, a strong dependence on these countries for the supply of the platinum itself. Moreover, when we go to the costs of a fuel cell stack system, then we can see, so this orange range here is related to the catalyst cost fraction. Then we can basically see that almost independent of the production rate of fuel cell stacks, you can see that the catalyst cost fraction is the most dominant factor here. And this is basically because the main cost of the catalyst that we have within a fuel cell system is related to just the pure elemental costs of the platinum by itself. And based on that, if we would like to reduce the costs of the overall fuel cell system, if we would like to go into this regime in terms of production rates, then of course we need to replace the platinum or really be able to lower it significantly in order to reduce further the costs of a fuel cell system. And when we have a closer look to the two electrochemical reactions, the hydrogen oxidation reaction and the oxygen reduction reaction, then we can basically see that the oxygen reduction reaction is quite inefficient. This you can see, what I plotted here is the potential, and here we have the standard potential for the oxygen reduction reaction, and here's the standard potential for the hydrogen oxidation reaction. And the red curve that goes up here is the real performance of a platinum catalyst material for the hydrogen oxidation reaction, and this gray dashed part here mimics the overpotential losses that you need in order to gain this current density here. When you look then for the oxygen reduction reaction, and this is basically the same current density in terms of absolute value, then you can see that the overpotential loss on the oxygen reduction reaction side is much larger. And based on that, most of the platinum is required for the oxygen reduction reaction. And that means if we are able to replace a platinum on our cathodic side, then we can basically enable a drastic reduction of the overall costs of a fuel cell system. And this, of course, would be nice, as it would enable the utilization in a broad range. So just to sum up, the aim is to replace the platinum-based catalyst materials on the cathodic side by our cheap and earth-abundant non-precious catalyst materials. So first of all, on the search of new catalysts, or as Christina announced on Twitter, can non-precious metal catalysts replace the platinum? And in relation to this, there are basically target values in relation to this that are defined, for instance, from the US Department of Energy. By the way, there is also from the US Department of Energy, for those of you who might not know, the so-called Electrochemical Consortium that explicitly works on the replacement of platinum-type catalyst material for fuel cell application. So they are probably to make some advertisement for this homepage, you can also look up a lot of strategies for the development of this type of catalyst material. For the non-precious catalyst materials, there are target values in relation to the activity that you should achieve. And this is basically because when we go for a fuel cell car, then of course we have a limited space where we can put in our fuel cell stack. And based on this, of course, you cannot just increase the absolute amount of the catalyst material and have a orders of magnitude larger stack in comparison to platinum. But at a certain point, you need to be able to fill it in to the given space, let's say. And based on that, the non-precious catalyst materials should reach ideally above 44 milliamps per square centimeter at 900 millivolts, if this is ER corrected, in a hydrogen and oxygen fuel cell, or for the real operation, which is then in hydrogen and air, they should reach 75 milliamps per square centimeter at 800 millivolt. So this is the target with respect to the activity, and with respect to the stability, the aim is that with respect to active site degradation, they should not lose, or they should lose less than 30 millivolts in order to obtain a current density of 0.8 amps per square centimeter. And the mass activity loss, which is induced by carbon oxidation, should be less than 40%. These degradation tests are basically related to some accelerated stress tests. I will later show you one example of such kind of protocols, how they basically can look like. So basically it is that you continuously cycle in a distinct potential window, and the potential windows in order to measure the active site degradation is a different one in comparison to the potential window for the carbon oxidation study. Okay, so if we would be able to reach these goals, then basically we are done and we can replace the platinum type catalyst material for fuel cells. This is of course probably not the end of the story, as of course then we also need to enable that also the synthesis strategy can be easily scaled up and things like that. But of course, this is like the first thing that we need to fulfill in order to make them applicable. For the preparation of FE&C catalyst materials, it's basically like making a cake. I guess every one of you has already done so. But of course, we use different recipes and different chemicals. So basically, you can use any type of iron source, nitrogen source, and carbon source. You mix them together and then you apply a temperature program in order to form your catalyst material. Within my group, we basically always perform also an additional acid leaching step in order to ensure that we get rid of side products that of course might also be formed during the high temperature pyrolysis. When you now like to optimize your catalyst preparations, and of course, let us assume you have a, let's say, state-of-the-art preparation approach. And now there are, of course, different ways how you can optimize it, for instance, by a variation of the composition, by the temperature, the time, the heating ramp, the gas flow, the gas atmosphere. All of these different factors during the heat treatment will basically affect the performance of the final catalyst material. As, by the way, also the acid leaching that we perform, also by that, of course, we will affect the performance of the catalyst. The aim is, of course, to get an improvement. So this is a polarization curve where you have the cell voltage plotted as a function of the current density. And as, of course, you'd like to maximize the current density at 0.8 volts, you prefer to go into this direction for the optimization of the catalyst material. The bottleneck for this type of preparation is that you need to find a good balance between the activity and the stability of the catalyst material. As, yeah, so this is a little bit more complex. I will probably not go here too much into detail in relation to this. So I already mentioned that the maximization of the current density at 0.8 volts is, of course, one of the targets for fuel cell application. And of course, if we would like to do so, then we need to understand how the current density is developed. And the current density by itself is basically a product of the number of active sites and the reaction speed. And then there is also a proportionality factor. But based on that, we have two, let's say, real chemical numbers, that is the site density, and the turnover frequency that determines the current density that we can achieve. That means when we would like to optimize our catalyst, we typically would like to go into this direction in order to maximize it for the site density and the turnover frequency. But very often we either go for higher site density or higher turnover frequency. So now we need to understand how we can basically determine the site density in this type of catalyst material. And that's indeed not as easy. We have a black catalyst powder, and in contrast to platinum, we do not have nanoparticles, but we have molecular centers which are integrated in the graphene sheets. The system is more or less highly amorphous, and in an ideal case, you will not see anything when you go for TEM imaging. At least nothing which is like really like by 100% ensured related to the activity of the system. And also in contrast to, for instance, platinum alloy catalyst material, where you can get some very nice ideas of strain effects and everything when you go for X-ray diffraction. These standard techniques are not applicable. But luckily, we have a lot of iron within our system. In these FENC catalyst materials. And based on that, of course, we can use Mössbauer spectroscopy for the structural identification of the catalyst. So Mössbauer spectroscopy can give you the fingerprint basically from the iron sites within the system. And what we have in a Mössbauer spectrum is that we plot our Mössbauer site. In this case, this is, for instance, a doublet with a velocity axis as the x-axis and the absorption as the y-axis. And basically, the x-axis is related to the energy, and the absorption is basically a measure for the intensity. These doublets are characterized by two parameters, that is the quadrupole splitting and the isomer shift. And these two values are quite important with respect to the characterization of the catalyst materials, because the isomer shift is related to the electron density on the iron centers. And this is basically affected by the spin and oxidation state. Based on that, we can get here, for instance, some ideas of the interaction between our catalytically active sites and the oxygen molecule or the intermediates which are formed during the reaction. And beside that, we have the quadrupole splitting. That is related or basically appears as soon as we have an inhomogeneous electron density distribution around our iron nucleus. Based on that, for instance, square planar coordination of our molecular centers or a five-fold coordination, you would be able to distinguish by the quadrupole splitting. But what is important to be mentioned is always in combination also with the isomer shift. You cannot really analyze these two parameters independently. Nevertheless, when we have these parameters, then basically we can get some nice information on the coordination environment and the electronic properties of our active sites. Based on this, let's say we would have the ideal case and we would just only have a doublet. Then, of course, the site density basically equals the overall amount of iron that we have within our catalyst material. Unfortunately, based on the heat treatment that we perform, it's more often that we have an overlay of different species. Sometimes we even see some sextets within our catalyst materials, or we might have some additional doublets, but only a distinct quantity might be related to the activity. And in that case, then of course, we need to multiply the iron content with the area, with the absorption area that is associated with the FeN4 environments that we assume as active sites in these type of catalyst materials. So Mössbauer spectroscopy can be performed ex situ or in situ. When we go for ex situ Mössbauer spectroscopy, we typically perform it on the catalyst powder. And this is very nice for basic comparison, for instance, of different preparation approaches. Like we have a catalyst that contains additionally some sextet species or not, what might be effect of the pyrolysis temperature, for instance. But what we always need to keep in mind is our catalysts are intended to reduce oxygen within the fuel cell. And based on that, of course, they have a very high affinity to oxygen. And as they are typically in contact with air, you might assume that the active sites already bind oxygen. That means they are in an oxygenated state. Besides ex situ Mössbauer spectroscopy, that, as I mentioned, helps to distinguish the different preparation approaches and, let's say, to see which one looks more optimal, we can also go for in situ Mössbauer spectroscopy, and that means a coupling of Mössbauer spectroscopy with electrochemistry. In this case, we might be able to, basically the measurements are performed on on the catalyst under applied conditions, different potentials, for instance, or maybe even different gas atmospheres. And based on that, we might be able to identify different coordination environments for the different states of operation within our experiment. What needs to be mentioned is that it is quite difficult to realize this, at least for our catalyst material. I mentioned we have a lot of iron inside, but a lot of iron means in this case something like 3 weight %. And as Mörsbauer spectroscopy is limited to one specific isotope of iron, we basically need always to work with fully enriched samples in order to enable this kind of experiment, what is quite expensive, but of course it gives us a lot of reasonable, nice insights. So now I would like to come to some results that we obtained. And the first part is related to the optimization of FENC, preparation. And these are basically results mainly obtained by Markus, but also from Vladi. And based on this, of course, I would like to mention this. So first of all, so this was like the beginning of Markus' PhD work, and I told him that basically we are searching for a new preparation route for the FENC catalyst materials that should enable not only a high activity, but also a good stability. And Markus did his master thesis within another institute in Germany, and he was working there on platinum type catalyst material, and put them basically on some surface functionalized CNTs. And based on that, he thought, okay, CNTs might be a good way in order to basically marry them to the FEN4 centers. And this was the idea that he then had for this very first synthesis strategies. The CNTs have, of course, the advantage that they are very good for the fuel cell stability, as they have a low reactivity. But of course, they are, due to this low reactivity, they are also worse for the attachment of this FEN4 centers. So he then thought that this surface functionalization that he also performed in order to get a better interaction between the CNTs and the platinum nanoparticles, he thought that this might be also a good strategy in order to directly bind the FEN4 centers to the surface functionalized CNTs, then to perform the pyrolysis in order to form then basically our final catalyst material. The surface functionalization was tried out with pyridine and indazole. In the next slides, I will basically focus only on the brief comparison between the non-functionalized CNT and the indazole functionalized CNTs. If you like to read the full story on this, then I just refer to the paper where, of course, also the pyridine and also some reference sample is included. So in the first comparison, we basically just compared the activity of the surface functionalized CNTs with the, so this X stands for the iron and additional nitrogen precursor that was used within the preparation of the catalyst material, in comparison to the just CNTs, again, of course, plus the iron and nitrogen precursor. First of all, when we were looking for the TEM images, then we were able to see that here what we see is basically CNT, and then somewhere beside there is the carbon framework with the FEN4 centers integrated. But for the surface functionalized CNTs, we basically get this carbon frames directly attached to the walls of the CNTs. This becomes also visible when you zoom out. Then you can really see that all of the CNTs look like that they would have these kind of spots on their surface, basically. These are the results from an RDE experiment, and in that case, you have the current density as a function of the potential. For the oxygen reduction reaction, we have a standard potential of 1.23 volts, and that means you expect a low onset potential. This would be like for the blue curve, whereas the onset potential for the CNT-based catalyst material is much worse in comparison to this one. So this was already a nice result, and we were already quite happy about this, specifically also when Markus then performed some accelerated stress test. So in this case, this was 10,000 cycles in a potential window between 0 volt and 1.2 volt, what is quite a lot. And what you can see is that even after this accelerated stress test, the performance of the modified catalyst material functionalized with the indazole prior to the heat treatment gave a very good durability of our catalyst material in comparison to the non-functionalized CNTs used within the synthesis. When we then analyzed the composition of the catalyst materials in order to identify whether we were able to improve the site density or the turnover frequency, what we were basically able to show is that, so this is a non-functionalized system. This is for the pyridine functionalization and this for the indazole functionalization. And as you can see by this functionalization, starting from the non-functionalized system, we are even able to increase the site density and the turnover frequency. And this was quite nice, as typically it's only one of the factors that you are basically able to improve. What so far I did not tell you is that unfortunately for this preparation, it's not really as easy to really scale up the site density. So the site density for this system is still, even after this improvement, much lower than in comparison to other FENC preparation strategies. Also, when we went for fuel cell application, basically this improvement, as we were able to see in the RDE experiment, does not really show up as nice during the fuel cell testing. But fortunately, this was a good starting point for the development of a new preparation strategy. And so you can see that this new preparation strategy enables orders of magnitude higher activity within the fuel cell. So during the last years, based on that, we obtained significant improvements for the activity of our non-precious catalyst materials, and specifically also the stability. So this is a potentiostatic test in hydrogen air at 0.5 volts. And there you can see that we get quite good stability with respect to what you typically observe for the FENC catalyst materials. To get some better idea, I plotted here really from the, let's say, leading publications in this range, the power density, let's say as a measure of the activity, as a function of the remaining activity after 20 or 100 or 50 hours of such kind of potentiostatic test. And what typically for this group of catalysts is observed is that you see this type of trend. So either you have a good activity, but then a very poor stability, or you have a good stability, but then typically you do not reach high current densities or high power densities. This is somehow really a kind of exception. So our point is more or less here in the middle in between, but we still already obtain some more results. So that means it looks like that we at least can also push a little bit more into this direction. So now I would like to move over for the active site identification. And this is basically related to the PhD work from Ling Mei Ni and Lotti, Charlotte Gallenkamp. Ling Mei is or was performing the in situ Mössbauer spectroscopic experiments that I will show, and Lotti was performing the theoretical calculations. Lotti is a joint PhD student, this I would also like to mention, together with Vera Krewald. So she has a Merck scholarship and is basically working in both groups, or between the two groups, as you prefer. So why would we like to identify the active sites? What I so far did not mention is for the oxygen reduction reactions, there are basically two pathways. We can either perform the direct oxygen reduction with the formation of water, or we can go for the indirect reduction of oxygen, either with only the formation of hydrogen peroxide, or in a so-called 2x2 electron transfer process with first the formation of hydrogen peroxide and then the further reduction to water. And of course, there's a question is, how does the active site look like, and whether we might have, for instance, two different types of active site, one for the direct reduction of oxygen, and let's say one for the hydrogen peroxide reduction, or maybe for the further reduction of hydrogen peroxide. In relation to this, we compared three different preparation routes. I would not really like to go here too much into detail, but the aim was basically to understand whether the changes that we might see during in situ Mössbauer spectroscopy are just only valid for one type of catalytic system, or whether we can basically see the same changes for different preparation routes. And based on that, as these three preparation routes are, let's say, representative for the three different main routes, either soft templated, carbon supported, or hard templated. We thought this is probably a good approach in order to get there some better insights to what extent the preparation route might also affect the spectroscopic outcome. So first of all, before I come to the results that we obtained for this catalyst material, I first like to give you a brief overview why we need to perform in situ Mössbauer spectroscopy. I already mentioned when I introduced Mössbauer spectroscopy that when you perform it ex situ, you basically measure the oxygenated state. And this is just an overview of 3 different FeN4 environments that, as you can see, can be distinguished by the oxidation state, but also by the local coordination environment and how the oxygen is attached. What you typically have for all of these states, independent on its oxidation or spin state, is that they form a doublet with a relatively equal isomer shift and quadrupole splitting. Based on that, it's more or less not possible to distinguish the different deoxygenated state related to these different transitions when you go for ex situ Mössbauer spectroscopy. So that means we need to know how here the deoxygenated state looks like in order to get some better idea which side seems most responsible for the catalytic reaction in our catalyst materials. And now to come back to our spoiler, the cell that we are using is a condom cell. So this has 2 reasons. We need basically to minimize absorption. So I already mentioned that in any way, we need to use highly enriched catalyst material in order to be able to measure them. And of course, we would like to minimize the absorption that we have within the water layer around our catalyst. And based on that, I told Ling Mei that it is really important that we can try to minimize it, and whether she can check whether there was like a work from Dan Schersen. I'm not sure whom of you probably knows him. And he was also performing some in situ Mössbauer spectroscopy on some other systems during the 80s. And he was talking about a collapsing polyurethane cell, I think it was. I do not really exactly remember this. Nonetheless, and we were checking for some bags, but the problem was always that they have some outer parts that can easily crash. And for the condom, you do not have this. And this is quite nice. And so we also needed to put this inside the report for our funding agency, as otherwise it would be hard to get the condoms funded by the funding agency. Nonetheless, this is a nice approach, and it really works out nicely for the investigation of this catalyst. So, talking sufficiently about the condom cell, this is again an RDE measurement, and this time I compare the scan in nitrogen and in oxygen. And now I would like to discuss what type of, let's say, states for our catalyst material we would basically expect in the different regions. So we have, first of all, a potential range which is above the onset potential. So the onset potential is basically when the oxygen reduction starts, and that is when we have here more negative current in comparison to the just nitrogen scan. Under such kind of conditions, we assume that our catalyst will be still within the oxygenated state, and that means still oxygen or OH or water might be attached to the surface of our catalyst. When we then go below the onset potential, but we keep our electrode under nitrogen, then we would basically assume that we are able to transfer the catalyst to the deoxygenated state. And if we would then even induce oxygen, then of course we would measure our catalyst under operation. This is marked here in gray, as I will just only focus on the comparison between the oxygenated and the deoxygenated state, and not go for the oxygen insertion in this case. So that means if we now just compare these 2 conditions with respect to our sites, then basically we have here the oxygenated versions and the deoxygenated versions. And if we now compare how the Mössbauer signatures of these deoxygenated versions would look like, then you can see that here we have now the chance to discriminate which sites seem to be present within the catalyst material. They have quite different Mössbauer parameters in terms of isomer shift or quadrupole splitting, and based on that we can distinguish them clearly. So this is a comparison between the oxygenated and the deoxygenated state for this one. And just to show you how this might develop without the contribution of the deoxygenated state, it looks like this. And if we then stepwise increase it, we go into this direction. And this, of course, you can play around also for the other 2 transitions, and you will obtain then this kind of graph. And based on that, we can basically summarize this graph into this one that basically shows that, for instance, here is no change, here this will decrease and this will increase, and based on that we have this code, let's say, for the arrows. And similarly, you can develop codes for the other two transitions in order to compare them then with the in situ Mörsbauer spectroscopic results. So these are then the spectra for the oxygenated and the deoxygenated state. First of all, you can see that the changes are not equally pronounced for the different catalyst materials. So that means we basically only have a partial transformation of the catalyst, obviously, to the deoxygenated state. Here are the original spectra, and here we have the different spectrum. And what you can basically see is that for two of the catalyst materials, we can identify two of these transitions, but for one of them, there are so far only indications and only small indications of one of these transitions. But we were not able to see this transition A, but only the transition B and C, which are associated to these two deoxygenated states. When we then investigated this a little bit further in combination with the DFT calculations, we can basically assume that for one of the catalytic sites, we have pyrolytic type coordination of the iron by 4 nitrogen atoms. And if we have the additional axial ligand, and this site is responsible for the direct reduction of oxygen, but also to a small quantity for the hydrogen peroxide formation. Whereas for the second site that we were able to identify, which is related to the transition C, this seemed to be more likely in a pyridinic type environment, but seemed a site which is capable of reducing the hydrogen peroxide further to oxygen. So this is then basically a slide to conclude this in situ work. So we have the one site which is responsible for the direct reduction of oxygen, but also with small amounts of hydrogen peroxide. And the hydrogen peroxide is then eventually either released or might get further desorbed and adsorbed and reduced to water. So in the last part of this work, I just like briefly to address some further developments. And these are works that were done by Stephen Powell and Steffen Haller. And first of all, a brief motivation for the work from Steffen. In a previous PhD work of my group, we were trying to investigate this MNC catalyst materials for the oxygen evolution reaction. So this is basically the summary of, let's say, the PhD work from Alish, and the pure cobalt and C catalyst material performed like this blue line that you can see here at the bottom. He then developed a NASA preparation approach, which is basically summarized here. And what he found was a quite good activity for the oxygen evolution reaction, but we needed then also to identify that this catalyst is very inhomogeneous in its composition. So it does not only contain cobalt in 4 centers, but also sulfides and metallic particles and oxidic species. And basically what it turned out was that this oxyhydroxide species are at the origin of the oxygen evolution reaction activity of this catalyst materials that were prepared here. We then performed, or basically this was based on postmortem XPS measurements. So that means basically the catalyst was measured in the initial state after 5 minutes and after 10 minutes. And then again, also after 60 minutes. And there we were then able to identify these oxyhydroxide species within the catalyst material. But nonetheless, this gave the idea that, of course, even enforcing that we might have some oxidic species, it is quite easy for this preparation, as if you do not perform any acid leaching, then you have side products that of course gets oxidized. And based on that, you have then a mixture of metal and 4 centers and some oxidic species. We thought this might be, of course, an easy way to prepare the catalyst, as you do not need to perform the acid leaching. And you can combine the benefits from the metal and 4 centers for the oxygen reduction reaction and the oxyhydroxide species for the oxygen evolution reaction, and then go as a bifunctional catalyst material for the metal air battery application. So Steffen then basically varied the different metal centers for this type of catalyst material. Here is the oxygen reduction reaction activity, and here's the activity for the oxygen evolution reaction. And there we can basically see that the effect of the metal center on the performance is much more pronounced when we go for the oxygen evolution reaction, where the cobalt case worked out best. And that was also why he selected the cobalt-based catalyst material for further optimization, and then also applied this in a metal air battery, so in a zinc air battery. So this is then the performance of the catalyst, where you can see that within these first typically between 6 and 10 cycles, we see unfortunately here an increase in the potential gap, but let's say the good point is that in the moment it looks like that this is more related to our cell design, as for a very different catalyst material we observe almost the exactly same trend here. So this seems not to be related to a let's say decrease of the cobalt type catalyst material. So last but not least, so I showed you now already some results for the oxygen reduction reaction, where the metal and 4 centers are active. I showed you also some results in relation to the oxygen evolution reaction, or basically the combination of both for the metal air battery application. What happens now when we would like to go here to the other potential window, to rather small potentials or even negative potentials, and that is then basically the regime for the CO2 reduction reaction. And if you go for the literature, then you can see that there is a lot of work popping up also for the application of the MNC catalyst materials for the CO2 reduction reaction. More prominent is basically the work on metallic catalyst materials for the CO2 reduction. And there is a quite early work by Hori et al., where a lot of different metals were investigated for the CO2 reduction reaction. And as you can see here, this is a very brief summary, of course, is that basically the selectivity of the formed product, the selectivity strongly depends on the selection of the metal. And this, of course, makes it questionable when we now go for the molecular type of active sites, whether we would observe like similar trends or whether they differ because we have this additional local environment provided by the nitrogen atoms. In relation to the MNC catalyst, as I mentioned, there is already a lot of work done. For instance, Varela et al. Investigated some Pani-based MNC catalyst materials. They were able to see basically quite similar trends in comparison to Hori, but when you have a closer look to their preparation and also compare it to other works where you find structural characterization of these type of catalyst, then you can see that there are a lot of impurity species present within this catalyst. So based on that, the question is whether it is indeed the metal and 4 centers which gives a similar trend, or whether these are the impurity species that gives the same trend as in Hori, because it is basically the same species as investigated by Hori. But what is also interesting was another work by Weng, who showed that there was a transformation of the kappa N4 centers to the metallic state under the reaction conditions for a kappa macrocycle. And there was again also a work in relation to a kappa NC catalyst, but again with the drawback that the preparation strategy might have led also to some side products based on the pyrolysis temperature and so on. So we basically then decided to select some model catalyst materials in order to minimize the side phase contributions. That means we used a carbon black in combination with very small quantities of a metal porphyrin. And the pyrolysis is also performed at low temperature at 600 degrees C. That is basically a temperature before the disintegration of the metal in 4 centers during the pyrolysis takes place. But in any way, we also performed an acid leaching step so that if there might be some side products formed, that we can leach them off before we then investigated the final catalyst materials. So these catalysts were investigated in a electrochemical setup with a gas diffusion electrode connected with a mass spectrometer, and also then by postmortem photoelectron spectroscopy in order to verify the structural changes during the reaction conditions, and basically then to compare also the data that we obtained to the selectivity data. So this is a manuscript that is currently in under investigation of Stephen Paul as first author, but it's a joint work with some other people from the Helmholtz Center in Berlin and from the Fachhochschule in Mittweida. So I would like to focus here on the postmortem XPS results. So here we have the current density as a function of potential for the kappa and C catalyst material. So the black closed curve here is the as measured current density, and the squares here represent the different points when the electrode was extracted for the postmortem XPS. And basically, how to explain? So let's say this red one was extracted as a potential of -1, but then we used a fresh electrode in order to prepare this green spectrum, which was then cycled, of course, up to this point. And there was a further point where basically it was first cycled into this direction and then cycled back to OCP in order to see the final state of the catalyst material. Here are the current density contributions to the different product formations on the kappa and C catalyst material. Here we have the kappa 2p spectra, and here it is the N1S spectra. And to make a long story short, in both spectra, you can basically see the transformation, at least of part of the kappa N4 centers to the metallic state. So this confirms the already existing data. But what is quite interesting to note is that this structural change coincides with the onset potential for the methane formation within this catalyst material. We then also performed a time-dependent variation, and here we have the different products. So what you can see when you measure over a distinct time is that at a certain point, the formation of methane goes down, and you see even more ethane within the product. Whereas the other products basically remain constant with respect to their intensity. And here is the fraction of the kappa 0 state within the catalyst material as a function of the electrolysis time at a potential of -1.5. And what we can basically see is that we have some kind of first order kinetics for the disintegration of the kappa N4 centers. And again, we can see that with an increase in the kappa 0 state, we have a decrease. First of all, we form the methane, but then over time, the methane formation decreases and we get even an increase in the formation of ethane for the catalyst material. So that means the product selectivity towards the hydrocarbon formation seem to be strongly connected with the formation of the metallic kappa 0 state, which is irreversible, as we were able to show by this scanning back approach. And based on that, it's not really the metal N4 center that seem to be related to the hydrocarbon formation, but it is just the metallic state. Probably you might be able to get a finer distribution of the kappa nanoparticles, but it's in any way not a molecular site which is related to the hydrocarbon formation for this type of catalyst material. We continued the study a little bit with comparison of other metal centers within the catalyst material. But in almost all cases, we were able to see that the metal center gets disintegrated at a potential of -1.5. In the next step, we will also investigate some further potentials in order to see, basically to identify the stability window for the molecular type of active sites, as so far it seems that it might be more the metallic state which is responsible for the different catalytic reactions. With this, I would like to come to my conclusions. First of all, I've shown you that the Fe and C catalyst materials are very promising for fuel cell applications. We can show some excellent performance data for our new preparation approach. Still, we need to go far before we can implement them in fuel cell cars. But I think if we keep some time, then we will also probably be able to do so. From in situ Mössbauer spectroscopy, we were able to discriminate two active sites, one for the direct reduction and one for the further reduction of hydrogen peroxide to water. These Me and C catalyst materials might also be interesting materials, for instance, for metal air battery applications in combination with some oxyhydroxide systems. When you go for the low potential regime, so far, at least if you go quite negative, you see an irreversible disintegration, but we need to investigate this further in order to see until which range they basically remain stable. And with this, I would like to thank you for your kind attention, and I'm happy to take over your questions.
Thank you very much, Ulrike. Very great talk. We have one question already in the chat, and I would like to ask, and now I can only say this name wrong, Arunachawa. Could you unmute yourself and ask your questions, please?
Yeah, Professor Kanan is actually at the Poly.
Right.
I guess he's the graduate chair.
Well, yeah. Nice presentation. So it was very insightful how the non-platinum catalyst for oxygen reduction in the PM fuel cells. So I was looking at one of the slides where you had the fuel cell perform polarization data, that the OCV was only about 0.9 volt, even though you used hydrogen and oxygen gases as the feed.
I guess you mean, just give me a second, and it's probably more easy to directly go for that slide.
Yeah.
You mean where I showed, so
it was a polarization data.
You mean this
hydrogen
one?
and oxygen gases. Yeah, I think that's the one on the right-hand side bottom. Yeah.
Yeah.
So what is the reason why for the lower OCV, even though you used hydrogen and oxygen, typically it is always above 1 volt?
So for the FENC, we do not see it quite above 1 volt. What you can observe is that, of course, you have a dependence on the humidity of the system. And these were some tests that were, let's say, quite in the early times after setting up our fuel cell system. So that means where probably it was not fully optimized. We still do not see, even when we go for hydrogen air application, we do not see that it goes up to 1 volt, but it depends a lot on the measurement conditions and the setups that we are using also.
Is it because you might have per hydroxyl ions in the open circuit conditions?
Hard to tell. So I could not tell you the exact reason for this. So this is basically also something where we are basically currently looking on in order to get it here further boosted to higher values. Okay.
Then I also wrote another one. It was mostly on the long-term stability. I think you had probably next slide or yeah, that's the one actually at the bottom. So you have 100 hours operation, and actually this is at 0.5 volt. But if you look at the data on the upper top, left, so at 0.5 volt, the current density is higher. Is it because that the voltage was the IR corrected? So
here it is ER corrected, here it's not ER. So here we start with 520, and here at 0.5 we have something like 600. Yeah, but here it is ER corrected, and here it is without ER correction.
Okay, that's right.
Yeah.
And then, so did you do any like a real long term? Because 100 hours is probably not a real long term, right?
So for this catalyst, we also went up to at least 200, and it looks quite stable. Okay. So it depends, of course, on what you call stable. But if it loses only something like 10 to 15% within 200 hours, I would call this relatively stable for an FENC catalyst material.
Yeah, right. And this kind of stability is probably not meeting the DOE requirement in terms of stability, right?
This is what?
This probably does not meet, or is it okay if, as per the DOE's stability?
So for the DOE stability, it is defined by the cycling. And as we did not perform cycling, but potentiostatic, but still in the literature, most of the work that you find is potentiostatic. And based on that, we selected this condition to have a better comparison to literature. Okay. Yeah, typically, these any transition metal catalyst, when you really look at for long term, there's always some kind of a corrosion or dissolution because the electrolyte is still acidic in nature. Yeah. So most of them have much lower stability, as it is also shown here.
Do you have any comparison with the platinum, especially on the probably CV or LSV data?
I certainly have on my computer, but I did not
Okay.
implement it for the presentation. So the platinum would be more like this, most likely.
Right, something like that, right?
So
Because
by
it's
the way,
IR
for the
corrected, so-
platinum, we also do not reach that OCP, which is so I think it's a let's say setup related
Probably, yeah. Okay.
problem and not related to our catalyst material that we do not reach it here much higher.
Okay. All right, wonderful. Thank you very much.
You're welcome.
Thank you. So Shannon wanted to ask a question, and then Carl can go next.
Great. Really nice talk, Ulrike. I was glad I was able to catch this. So thanks for tweeting about it, Christina.
You're welcome. Thanks for hopping on.
Yeah. So we're actually collaborating with Ulrike on some Mossbauer on some of our work we're doing. So this is really great to see. So anyways, I had some questions about, what other characterization have people done on these iron, graphitic iron sites? If you do really long-term, have people looked at like leaching rates? How tightly is the iron bound in there? Have people done like the online ICP-MS type experiments and look at those sort of things, I guess? So kind of on the practical side, like people really looked at, what's going on under those ORR conditions, because it's pretty aggressive. Also the carbon support. And then the other thing I wanted to ask about is, there's lots of discussions about sort of what's the nominal oxidation state. And is there any evidence of like minority species in your samples that access higher oxidation states under ORR conditions and sort of nominally 3+ or anything like that? So those are the two questions I have.
So first of all, there is like a work from Karl and so Karl Meyerhofer and Frédéric Jaoun related to the online leaching rate, let's say. But now there is a but, because this was performed on a catalyst that was prepared in 950 degrees C, but without an acid leaching. And based on that, due to 15 years of experience with the preparation of this type of catalyst material, you have there some side phases inside. And based on that, it is of course quite hard to know to what extent the iron leaching that you can see is in parts at least related to this side products, or whether it is indeed coming from the FEN4 center. So that means basically one would need to repeat this then for a catalyst which is at least acid leached in advance before, in order to see, let's say, the true leaching rate during operation.
Okay.
Yeah.
Should we wrap it up?
Probably this is done by the CIA. As
Yeah,
I mentioned, the
we should. Yeah, we are maybe 5 minutes over. Yeah, let's wrap. Let's call it a day. Yeah.
Okay.
Yeah, so it was really nice to be here, even though for at least the technical problems did not happen during the presentation, but only during the questioning. So it was really nice to be here, and I will also join for some other talks soon. Yeah, thank you.
Thank you.
Bye-bye.